Hello viewers, welcome to my channel IITJ Olympiads and AP Physics with Ambarish. And today I have brought a very interesting topic for all of you. That is, why is a Carnot engine most efficient? So many students know this as a fact that Carnot engine is most efficient, but then what exactly does it mean that it has got maximum efficiency? And moreover, many sharp students, they feel intrigued by it that why can't any engine be more efficient than the Carnot engine between two given temperatures. So today I have brought proof for this, and I'm sure you are going to enjoy this geometrical proof of this fact that Carnot engine is most efficient. So to make it very specific, let me state the exact statement that we are going to prove. Okay, so I've stated in the question format. So the question is, of all the reversible cycles operating between a certain maximum and minimum temperature, prove that no cycle can have an efficiency greater than the Carnot cycle. So what is fixed here? The maximum temperature is fixed, the maximum temperature and the minimum temperature is fixed, and out of this we can have so many cycles between that maximum and minimum temperatures, and we have to prove that Carnot cycle is most efficient of all of them. So how do we go about doing it? So let's see. So first of all, I am going to define what is the meaning of entropy. Thermodynamic definition, of course, this is a statistical definition of entropy that we are not going to discuss here. I am just going to discuss the or rather state the thermodynamic definition of entropy. That is, for any process, the change in entropy is defined as ds is equal to dq upon t reversible. So if any gas is going from one state to another, we need to find the integral of dq by t, and even if it's an irreversible process, we have to find a path with a reversible path between first state and the second state to calculate the entropy. Okay, so this is the basic definition of entropy. Okay, so accordingly we can say that for reversible adiabatic process, entropy is constant. Why? Because if it's a reversible adiabatic process, then dq is 0, right? Adiabatic process by definition means that no heat is being supplied, and anyway it's a reversible process, therefore ds is 0, and if ds is 0, obviously that means change in entropy is 0 or entropy is constant. So we can also call any reversible adiabatic process as isentropic process. Okay, so how does a Carnot cycle look like? So all of you know that Carnot cycle has got two adiabatic curves and two isotherms. So this is what a Carnot cycle looks like on a PV graph, and accordingly on a TS or temperature versus entropy graph, you know that isothermal process is going to look like a horizontal line, and the adiabatic processes, because they are isentropic processes, they are going to look like vertical lines. So this is how a Carnot cycle will look like on a TS graph, a perfect rectangle. Okay, so so reversible adiabatic process will be isentropic process, right? Any reversible, I should have called it reversible adiabatic. Okay, I'll just add a word, adiabatic. Okay, any reversible adiabatic process, that's isentropic process. Okay, accordingly, according to equation 1, for any reversible process, dq tds delta q is integral of tds. Okay, which means that heat supplied in any process is equal to the area enclosed under the TS graph. Okay, so just if you rearrange this equation, you take t over there and you can say that dq is tds, and integral tds by definition of integral, it means that area under the t versus s graph. So therefore in any process, if you want to find out how much is the heat supplied, so you just take the area under the graph. For example, from 1 to 2, the heat supplied is just this area. This area is the heat supplied in the process 1 to 2. Similarly, and yes, and if the entropy is increasing, if ds is positive, then obviously heat is being supplied to the system, and if entropy is decreasing, then ds is negative and obviously heat is being rejected from the system. So if you want, you can find out from 1 to 2, this area is the heat supplied, and from 3 to 4, this much area is the rejected heat, right? And obviously here there is isentropic process, there is no heat absorption, therefore area under this vertical line is 0, area under this vertical line is 0, because there is no heat being supplied or removed from the system. Okay, so this was the second fact I wanted to state. What is that? The heat supplied in any process is equal to the area under the TS graph. Okay, and then the third fact that I am going to state, this is a common knowledge, every student knows this. from the lectures on thermodynamics, that is, for any arbitrary cycle the efficiency is given by simply delta W divided by delta Q plus. So what delta W is the total work done by the system here, and delta Q plus is the positive heat supplied to the system. Here we do not count the heat rejected by the system. For example, if we supply 1000 joule heat and then system rejects 200 joule, then I won't say that heat supplied is 800. Positive heat supplied is still 1000 joule. So I do not subtract the rejected heat here. So this is what my efficiency is. Okay, so efficiency of any system is cycle is delta W upon delta Q plus. Okay, where delta W is the total work done by the system and delta Q plus is the positive heat supplied to the system. And now if delta Q minus is the heat rejected by the system in the cycle, then we can also write that work done by the system should be equal to the positive heat supplied minus the heat rejected by the system, right? Delta Q minus is the magnitude of heat rejected by the system. So obviously when you are going in a cyclic process and you are coming back to the same position again and again in the process, that means what? Delta U is 0. If delta U is 0, that means what? Total work done by the system must be equal to total heat supplied to the system. And what is the total heat supplied to the system? That is the positive heat supplied and minus the heat rejected. So this is the total heat supplied to the system, which is equal to the work done in the cycle, right? So delta W is delta Q plus minus delta Q minus. Delta Q minus is the magnitude of heat rejected by the system. Okay, so by conservation of energy or first law of thermodynamics, we can say this. Now if we consider any arbitrary cycle on the TS diagram, let us say this is some arbitrary cycle. I have drawn it like an ellipse, but need not be ellipse, it could be even something like that, or whatever your favorite shape. You can make a cycle like that on the TS diagram, and we are considering that cycle. So so when entropy is increasing, I said that positive heat was being supplied to the system, and when entropy is decreasing, the heat was being rejected, as I stated earlier. So delta Q plus in this cycle is given by what? This is the yellow shaded region, right? In this cycle, from, let's say I name this points, let us say I call this as point A and I call this point B. So when I am going from A to B along this, so area enclosed under the graph is this much, right? And this is because from A to B entropy is increasing, therefore this is the positive heat supplied to the system. So that's what I've shown. So this yellow marked area is the positive heat that is supplied to the system. Okay, because here the entropy was least and here the entropy is maximum, and I have drawn the vertical tangents and taken the area between the vertical tangents, right? So this is the positive heat supplied to the system. Okay, now similarly, how much heat is rejected by the system? So you see again between the vertical tangents, I can say this is the point of maximum entropy and this is the point of minimum entropy. So from here to here heat is being rejected, right? So I have taken this area. So this area magnitude is the magnitude of heat rejected by the system, right? So this green shaded area, right? So this is the positive heat supplied and this is the negative heat supplied. Okay, and now what is the efficiency from 1 and 2? See, what are the equations 1 and 2? So equation 2 is delta Q minus is the delta W, and eta is delta W divided by delta Q plus. So using these two equations, I can say that the efficiency is simply what? Efficiency is delta Q plus minus delta Q minus divided by delta Q plus, which is, if you divide this denominator, divide by this denominator, you get this 1 minus delta Q minus divided by delta Q plus. Okay, and this is what? This is basically delta Q minus is the green shaded area and delta Q plus is the yellow shaded area. So efficiency is 1 minus the green shaded area divided by the yellow shaded area, right? So this is your efficiency of this cycle. Okay, I'm going to state it again in a little while. Okay, so this is what I've written. Eta is 1 minus A2 by A1. So this I've called as A2 and this I've called as A1. So I hope this much is clear for the efficiency of this cycle, the arbitrary cycle. Now let us enclose our cycle into a Carnot cycle for comparing the efficiencies. Now between the same temperatures, I can also have, between the same maximum and minimum temperatures, I can also have a rectangle, right? And this rectangle will represent the corresponding Carnot cycle between the same maximum and minimum temperatures, right? So now positive heat supplied from Carnot cycle is given by this orange shaded area, right? Because when we are going from here to here, the entropy is increasing, so this is the positive heat supplied. So that's what I have shown. This is the orange shaded area is the delta Q positive. or I am using the primed variables for Carnot cycle. So this is A1 prime, which is delta Q plus prime, which is the positive heat supplied in the Carnot cycle, right? Similarly, negative heat rejected in Carnot cycle, the magenta shaded area, this. So this is the place where the entropy is decreasing, right? This was vertical lines were isentropic lines, right? So this magenta shaded area is the area where the heat is being rejected, okay? So so now, since I have shown all the four areas, let's look at all the four cycles, all the four diagrams together. So we can see that for the arbitrary cycle, the yellow shaded is the positive heat supplied, and orange shaded is the positive heat supplied for the corresponding Carnot cycle. And clearly we can see that orange shaded area is greater than the yellow shaded area, because it's going, see, the orange is going below this ellipse kind of line. So obviously this orange area must be greater than the yellow area, right? And similarly, if you see the heat rejected, if you see in the green shaded area, is greater than the pink shaded, the magenta shaded area, right? So we can say that the arbitrary cycle rejects more heat and accepts less heat for the same temperature, right? It rejects more heat and it accepts less heat, whereas the Carnot cycle, it accepts more heat and rejects less heat, right? So that means what? Here also you can see intuitively, even without any mathematics, you can directly see that this must be doing more amount of work, okay? So now, but let's do it mathematically. So efficiency is 1 minus delta Q minus divided by delta Q plus, and that is 1 minus A2 by A1. So this is A2 and this is A1. So this is the efficiency for the arbitrary cycle. And what about Carnot cycle? For Carnot cycle, it is 1 minus delta Q minus prime divided by delta Q plus prime. So that is 1 minus A2 prime divided by A1 prime, okay? Now it can be readily seen that A2 prime is less than A2. So where is A2 prime? This A2 prime is less than A2, okay? And A1 prime is greater than A1. So this is your A1 prime and this is greater than A1, okay? Accordingly, I can say that A2 prime upon A1 prime. So this is lesser and this is greater, and so their ratio becomes even smaller, right? So A2 prime upon A1 prime is less than A2 by A1, okay? And accordingly, if you subtract from 1, the inequality will change the sign. When you multiply any inequality by minus 1, it changes the sign, right? So multiply both sides by minus 1 and add a 1. So I can say that 1 minus A2 prime upon A1 prime is greater than 1 minus A2 by A1. Okay, and what is this? This is nothing but efficiency of the primed cycle, that is Carnot cycle, and this is the efficiency of the general cycle, okay? So we can see that eta prime, that is Carnot efficiency, is greater than the efficiency of a general cycle, okay? So maximum efficiency is that of Carnot cycle between all cycles that are operating between a given maximum temperature and a given minimum temperature, okay? It does not matter what type of arbitrary reversible cycle you choose, okay? So that was the cute geometrical proof of this fact for maximum efficiency of Carnot engine. I hope you enjoyed this video, and if you did enjoy my analysis, please do give it a thumbs up, and please do share it with as many friends as possible through various WhatsApp groups, Telegram groups, or Discord servers, or Facebook, or whatever media you use for collaborating with your fellow students. And if you have not already subscribed to my channel, please do subscribe to my channel. My channel is not monetized. It's the love that I receive from you people that drives me to do more videos, and I hope you will help me grow this channel. Please do keep coming back to my channel for more awesome stuff. That's all for this video, and see you in the next one.